Alright, so just let me show you something. I go to the Maths Learning Centres page.
Oh, where's the video actually
Past years. Similar to this, but even longer. Sorry? Did I? Ah, sorry, wrong thing. I put it on the laptop rather than the install computer. So there's one here on metric spaces from last year, where I did lots of stuff. Where I talked about the various, open and closed and that sort of thing. And I think right at the end I got to the contraction mapping theorem, and it's probably time to do that now. So give me a second to just quickly look up the exact statement thereof. Okay, I'm going to do the contraction mapping theorem. I'm just going to do it, and we'll see what we get. Okay. And what I'll do is I'll add this video to this part of the page that says metric spaces. So that's the whole point that I was trying to make there.
I got the notes from last year. Did you need them?
I've got the notes I did from last year too. Okay, so the contraction mapping theorem says if you have a contraction mapping, then it has a unique fixed point. Not that there is a specific definition of contraction mapping, but that's what it means. And that's how I think about it. I have a function, which is a contraction. I have a mapping, which is a contraction, and it has a unique fixed point. So in my head, this is what I think. A mapping, which is a contraction. So a contraction mapping has a unique fixed point. Where a fixed point is a point that doesn't move when you do the mapping. So in my head, I'll draw a picture of it in a second, but the actual statement of the theorem says that you have a complete, just a second, sorry. Alright, so XD is a metric space. And F sends X to itself. Sorry, and F sends X to itself. Okay, so suppose XD is a metric space and F is a function which sends X to itself, and we have three things. If X is a complete metric space and no, sorry, two things. F is a complete metric space, that's important. And there is a number k such that the distance between f of x and f of y is less than or equal to k of the distance between x and y. So there is k which is less than 1, such that the distance between the function values at 2 points is less than or equal to k times the distance between the original 2 points for all x and y in the metric space. Then there is a unique point x in x with f of x is equal to x. That is the contraction mapping theorem. So mapping, this bit here is saying that the mapping is a contraction, and this is a fixed point here. So a fixed point is a point that doesn't move. So here's the picture of it in my head. Here's x, which is my metric space to begin with. And here's x again afterwards. And so we have a before and after picture. And the concept is that no matter which 2 points I pick before, which have a distance between them, afterwards, no matter where they are closer together than they were before. But not just any closer, this distance here is less than or equal to k times the original distance. Okay, so however far apart x and y before, afterwards f of x and f of y are closer together because they are less than or equal to k times d and k is less than 1. So that k is like a percentage, so perhaps it's 80%. So it could be saying that no matter how far apart they were before, afterwards they are no more than 80% of the distance apart that they were before. And that's called a contraction because everything is closer together than it was before. Things are contracting. And what they're saying is that there has to exist somewhere in there a point that is in exactly the same spot that it was before. Okay? That's not coming up. That's my fixed point. So this point is in the same spot. It's exactly where it used to be. And there's exactly one point that is in the same spot as it was before. But it does have to have this property of completeness. So we need to know what complete means. Complete means that all of the Cauchy sequences converge inside X. I believe that's the definition of complete. Okay, so there is no Cauchy sequences don't have to converge in a metric space. It is possible to have a sequence where the terms are closer to each other, but there is no limit that they are close to. Sorry. All Cauchy sequences converge in X. It's possible to have a point, the sequences that get closer to each other but don't have a limit that they get close to. Usually it's to do with that point being missing and you would expect it to be there. So the rational numbers, for example, as a metric space are not complete because I can have sequences of wholly rational numbers, which are all fractions, and they can approach an irrational number which isn't there in the rational numbers. So I can have a number like root 2, it can be 1, 1.4, 1.41, 1.414, 1.4142, and those are all rational numbers because I can write them as fractions, and they get closer and closer and closer to each other, and they would get closer to a number which would be root 2, but root 2 isn't in the rational numbers, so the rational numbers aren't complete. There's a point missing, which is where that sequence goes. Okay, so we need to, in our proof, use the fact that it is complete at least once, because otherwise we wouldn't need that in our proof. We wouldn't need it in the theorem. So we must use the completeness of my metric space at least once, which means I have to use a Cauchy sequence in there somewhere. Probably. Because that's what complete means. And I have to use this fact about distances getting smaller. And somehow I have to show that it is possible to have an x that does this, so I'm going to have to tell the reader how to find what x is, because otherwise I either have to suppose that there isn't an x and contradict myself, or I have to tell the reader what x is. So it might be easier to suppose that there isn't an x and see what we get. However, it might not be. It might be easier to actually construct x. My instinct tells me that if I'm to use the fact that sequences, that the metric space is complete, which means that all the limits of sequences exist, the quickest way to find out what x, to tell the reader what x is to tell them that it is the limit of a sequence. Because you know that the limit of sequences exist, of Cauchy sequence exists. So if I can find a Cauchy sequence, tell the reader about a Cauchy sequence, and then make that Cauchy sequence converge, and then say, that thing that it converges to, that is my x, that is the fixed point. So that sounds like a good idea. And that sort of matches with the idea of what a contraction mapping theorem, a contraction mapping should do, because if I'm going to draw a picture of my metric space, since everything gets closer together, like after I've done the contraction, if I take the whole metric space, it should only be like k% of the size afterwards. If I do the contraction on the entire metric space, contraction on the whole metric space, it should be smaller. And if I do the contraction on the whole metric space again, f squared, which means I've done f twice, it should be smaller again. And if I do the whole metric, the contraction on the whole metric space again, it should get smaller and smaller until it eventually ends up at a single point in the middle, which is my fixed point. That's the idea. So what I could do is I could pick a point here and then follow it as it goes along. And if I follow that point, I should be able to make a sequence that converges to the x in the middle, which is my fixed point. That's what I'm going to attempt to do. All right. I'm going to cheat a little and try and remember what I did last year, a whole year ago.
Try it a different way.
Yeah, I won't do exactly what I did last year because that didn't work. Which sequence am I making here? Okay. So what I'm going to do is I'm actually going to pick any point at all. X naught. So here's my proof. Alright? F of x naught, x1 to be f of x naught, x2 to be f of x1, x3 to be f of x2, etc. That's my sequence. I'm going to show that that sequence, x0, x1, x2, x3, etc., is a Cauchy sequence and therefore has a limit. And I'm going to show that the limit of that sequence is a fixed point. Okay. And what I'm going to do is, first I'm going to need to show something about how things that are close to each other, how they get closer together. So before I can show that that's a Cauchy sequence, I'm going to have to show what the contraction does if you apply it multiple times. Okay. So sorry, it's M. No, you're allowed to leave that off. We'll show that this is a Cauchy sequence. So the definition of a Cauchy sequence is that the two different members of the sequence, that given any epsilon, there is an n such that if you choose two members of the sequence after that n, they're that close together. Does that sound right? Cauchy sequences, like there's an n, capital N and a capital N plus 1, n plus anything. Let me just go back and see if I can find the definition of Cauchy. Functions, closed. Sequence is Cauchy. Okay, yep. So to show that it's Cauchy, I need to show that for any epsilon greater than 0, there is an n in n such that the distance between xn and xm is less than epsilon for all m and n greater than or equal to capital M. That's the definition of Cauchy. So I need to, now let's see, xn and xm are both f acted upon x0 enough times. And so what I really need to do is know what happens when I enact f upon things enough times. Okay, give me a second, I'm just thinking about it. Well, I'm looking at the one in the notes, and it doesn't make any sense to me. Which happened last year. Oh no, it's okay. I'm all good. Okay. Right. So I would like to show that this is less than epsilon for any given epsilon. So let's think about this here. Okay? So let's see. dxn and dxm for any n and m and n in n in capital, in the integers, in natural numbers, sorry, this is d of f like that, because that's what this is. Back here, this is f squared of x naught, and this is f cubed of x naught, because it's doing f 3 times. Okay, so I know that if this is less than or equal to taking off an f out of here. I know that when I do f, everything's closer together than they were before. So if I remove one of the f's from this, what was the definition? Yeah, so if I remove the f's here, the distance is smaller than it was before without the f. So I could remove f's from either of these, but my problem is that if m is more than so I could remove an f from both, and I'll have fn minus 1, fm minus 1 x naught, and I could get all the way down to x naught on whichever of these was the smaller one. And then I have x naught and something that's f to the something. The problem with that is I don't know how far apart that is from x naught. And so what I need to do is somehow get down to a distance that doesn't rely on m or n. And if I did that trick of pulling out an f from that, I will get down to like f of m minus n or something, and that relies on both m and n. So I need to get down to something that, well, it doesn't rely on it in a way that I can't predict. So what I can do is I can use the triangle inequality. And do this trick here. Okay. Give me a second. Okay, this is not necessarily in the order that I would write it, but I'm trying to remember how to do it. So if I had just two random points, I know that because of the triangle inequality, I could figure out this. So I'm thinking I've got x and y, and I can put in, instead of that I've used the triangle inequality twice technically, I put in 2 points in between. So I'm thinking I've got x and y, and then putting in f of x and f of y in between them. Like that. So I'm saying the distance from x to y is less than or equal to the distance from x to f of x, the distance from f of x to f of y, and the distance from f of y to y. Which means that this is less than or equal to d of x f of x. And this is k. Because we know that d of f of x f of y is less than or equal to k times d of xy, according to the contraction, the fact that it's a contraction. So let's subtract this from both sides. Yep.
For, like when you did it last time, you supposed that there were 2 points and then you did dfx and then dfy.
Did I? This might work out better.
Okay.
I'm following what's going on here. And so d of xy minus k d of xy. Like that. And I can bring the dxy out of this. That's a plus, sorry. And I can divide both sides by 1 minus k. Now, k being less than 1 means that 1 minus k is a positive number and this will still work. Beautiful. Right. So let's see what that means for my xn and xm. So, I'll copy what I had before. So we know that dxn xm is d of f to the n x naught, f to the m x naught, and we can use this rule that we just did to say that is less than or equal to d of f n x naught f n x naught plus d f m x naught f m x naught over 1 minus k. So what I've done is I've put x n f n x naught in this spot for x, and f m x naught in this spot for y. Right. So let's just Right, so f of fm is f of m plus 1. Just to make it cleaner for myself, I could have written that first, but that's how I was working on it. So here's the thing. I know that if I pull an f out of this, it'll put a k in front. Okay? These both have an n. I can pull out an f, and I know that when I pull out an f, according to the contraction rule, they've both got an f. If I remove the f, it's equivalent to doing a k, timesing by k. So I get k, and that will take it down to n minus 1 and n. And then I'll get another k, so k squared, and I'll take it to n minus 2 and n minus 1. And then I can get a k, another k, and I'll take it to n minus 3 and n minus 2. And so I'm going to remove n lots of that, and I'll get the diff f. I will just remove all of them and leave me with x naught, f of x naught there. And this one will be k to the m, x naught, f of x naught. And I have successfully removed my k's from being inside, my m's and n's from being inside the d's. So now let's see, we get, they both have a dx naught fx naught. One minus k.
When you look at it, I can't see the top lines.
Right, here's the thing. Now we're good. If n and m are large enough, then k to the n and k to the m will be quite small. 1 minus k is a fixed number. So if I can make n and m big enough, then I can make this bit as small as I like, which means I can make this whole thing to be less than epsilon if I want to. So as n and m go to infinity, k to the n and k to the m go to 0. So therefore, that thing goes to 0. If n and m are both large, the distance between xn and xm will be less than epsilon for any given epsilon. Enough. Because this thing goes to 0. Because this thing is close, approaches 0 as both n and m increase. As long as you make n and m big enough, it will work. And so therefore the sequence is Cauchy. And I think you're allowed to use that sort of argument. Right. Hence, now, since x is closed, or not closed, since x is complete, the sequence has a limit. Call this limit x. And we have a couple of nuances that need to be fixed here. This is where your lecture notes, typed lecture notes finish. It says, well, this is your fixed point. But it didn't actually show that this point was fixed. And so that's the tricky bit that isn't in the notes and isn't in my notes from last year's seminar. I'm just going to check something about the function f. Oh, I was hoping that the function f was continuous, because a continuous function acted upon a sequence converges to the function on the limit.
Can we just assume that?
Well, you can probably prove that it's continuous. But you could assume it. If it was a continuous function, you could go, well, f of xn is actually just the same sequence again, starting one step later, because they're all already f of the previous one. So the sequence xn n equals 0 to infinity is the same as the sequence f of xn from n equals 1 to infinity. Crap. No. The sequence from 1 to infinity is the same as f of xn from 0 to infinity. So if I start the sequence at 1 instead of at 0, it still converges to the same place, and each of them is f of the one before them. And if f was continuous, that would be, if f is continuous, f of xn will go to f of the limit as n goes to infinity of xn, which is f of x. But we already know that f of xn is just x, the same sequence as xn, which goes to x, and so therefore f of x equals x. Yeah. Alternatively, you could show that it's unique. Yeah. We haven't yet shown that it's unique either, sadly. We've shown that it's fixed, but we haven't shown it's unique, which distresses me. Your lecturer didn't show it was unique in the lecture notes. So maybe it's okay. To show something's unique, the usual way is to suppose that there's two of them and show that they're equal to each other.
He might have done something different in the actual lecture. Notes, and he might have done that, but I'll try and find it.
Alternatively, we could show that no matter which point we start with, we always end up at the same place. Because then if we start from any point, we always end up at the, like, x0 was just a random point. We could show that if we start from any point, we always end up at the same position. Have you got any results about sequences getting closer to each other? Oh, no. Ooh, yeah. So if you started at some other point, say x, I'm just going to think about this for a second. I'll put it on another bit of paper. So if you have like xn and x, you know that the distance between xn and x approaches 0 as n goes to infinity because the limit does actually exist. Given the sequence does actually converge to x, you know that this goes to 0 as n goes to infinity. And you know that the distance between that proves it's unique as well. Well, I mean, that proves that f of x is fixed. I've got a different proof that f of x is fixed. We know that xn x goes to 0 as n goes to infinity because it converges to x. When a sequence converges, each term gets closer to the limit. Since the limit as n goes to infinity of xn is x, the distance between xn and x goes to 0 as n goes to infinity. Now the distance between f of x and xn is the same as the distance between f of x and f of xn minus 1, which is less than or equal to k times the distance between x and xn minus 1, because it's a contraction, which goes to 0. As n goes to infinity, which we knew. So therefore, the limit as n goes to infinity of xn is also f of x. And a sequence can only have one limit. So we don't need to do the continuous function thing. We can just use the fact that a sequence can only have one limit.
So we don't do the thing before.
No. And this should do the trick for showing it's unique as well. Because if you had two of them that were both fixed,
Would that have to be the same thing? Would that be similar to the
then consider the distance between x and y, right? That would be the same as the distance between f of x and f of y, right? Which would be less than or equal to k of the distance between x and y, because it's a contraction. And so I'd have 1 minus k, I'd have d of xy minus k d of xy would be less than or equal to 0. So 1 minus k of d of xy would be less than or equal to 0, which means d of xy would be less than or equal to 0, which means that d of xy would be equal to 0 because it can't be less than 0 because it's a distance. So therefore x equals y. So we have it now. We found a point, which was the limit of the sequence. We showed that the point was fixed, and we showed that there can't be two points that are fixed, there's only one. I'm sure there are other ways. But this way is a way that we have. So the key difference between this and what is in the printed notes, it may not be different to what was in the actual lectures, is that I have gone to the trouble of showing that the limit of that sequence is actually fixed and is actually the unique, and the fixed point that we found is the unique fixed point.
That would be the end of the proof, wouldn't it?
Yep.
That's contraction mapping, and including Cauchy sequence as well.
Yes, because we used the contraction multiple times, and we used a Kochi sequence to construct the point x. So we've used the fact that it's complete, and we've used the fact that it's a contraction multiple times, and so the proof is done, and we've gotten to the end. We have shown that there is a fixed point because we've told the reader what that fixed point is. We've shown that it really is fixed, and we've shown that it's unique, which was the theorem, a unique fixed point that does exist. Sorry? So if I was going to attempt to remember such a theorem, such a proof, I mean, the crux of the proof is this thing where we had to try and... this was a very clever trick here where we managed to somehow turn our xn and xm into something that was about two that were one apart from each other. Xn and xn plus 1. Because then we were able to actually use the theorem to get all the way down to x naught and f of x naught. Yeah. There's probably an easier proof. Though I dare say any proof that you would have those last two bits roughly the same. It's that first bit of constructing a Cauchy sequence that is the hard bit.
This is exactly what you just done now, basically.
Yes.
The fixed point, but you did that again.
I did at the beginning. Oh. Well, it seemed like the easiest part, so I did it first last time. So last year I did that the point is unique bit first because it seemed like the easiest part to do. But the point is that, yeah, that only shows that if there is one, there's only one, but it doesn't show you that there is one, so you've got to find that point by constructing the Cauchy sequence that converges to it. Did you want me to do the proof that a convergent sequence is Cauchy? Because that's one of the ones you were asking.
It was that proof that every convergent sequence is a Cauchy sequence.
Prove that a convergent sequence is Cauchy. That's what I'm going to attempt to prove. Yeah, that every convergent sequence is Cauchy, I guess. So I would say suppose or let so suppose that converges to x. I would like to show that this sequence is actually Cauchy, which means that I would need to do something like let epsilon be something greater than 0, and then I would need to somewhere along the line describe an capital N and show that the distance between xn and xm is less than epsilon as long as n and m are greater than capital N. That's what I would need to do. So somewhere along the lines in here I'm going to have to say what n is. And then I'm going to have to find the distance between xn and xn, do some working and show that it's less than epsilon. So n and m greater than or equal to capital N. That's what I'm going to have to do somewhere along the roads. I do know that if epsilon is greater than 0, I know that xn approaches x. I need to say what n is.
So that's what we did before. And that shows that the one that you picked is convergent and is Cauchy.
This is a whole new question.
But that doesn't vicariously prove it for every one.
No. Because the one that we had before was a Cauchy sequence that we assumed converged because it was in a complete metric space. But we're going the other way. We're going it converges and we want to make it Cauchy. But converging means that no matter how close I want to be to x, there is a capital N that makes me, that if I'm further away out than that xn, so I can do this. So there is an n in the natural numbers such that the distance between xn and the limit is less than epsilon for all n greater than or equal to capital N. I know that's true because it converges. And that's the definition of converging. So we do have an n. We found a capital N. Perhaps we can use this capital N. Well, we need an xm as well, so why don't we choose so suppose n and m are both greater than or equal to capital N, then what we want to show is that the distance between xn and xm is less than epsilon, because that's what it would mean to be Cauchy. Alright, so somewhere along the lines, I need this to be strictly less than epsilon. But I only know about the distance between xn and x, and xm and x, but I can put an x in by doing the triangle inequality. You can always put an x, another number, another point in the middle using the triangle inequality, and it'll be a less than or equal to. Well, this here is less than epsilon, because that's here, and this here is less than epsilon, and so I get that xn, xm is less than 2 epsilon, so I really need to choose this back here to be epsilon on 2. Because if I go back and fix this to be epsilon on 2, then I can say that the distance between xn and x is less than epsilon on 2, and the distance between x and xm is also less than epsilon on 2, which is epsilon. And so therefore, dxn xm is less than epsilon for all n and m greater than or equal to this capital N. So the sequence is Cauchy. End of proof. I don't know how your lecturer likes to end proofs.
Squares.
The black square box.
My wife says that you should end a proof like this. Or possibly like this. But we shall put a square box.
Is it Q?
QED.
QED.
Which means quad erat demonstratum,
Yeah.
which means which was what we were trying to show. So there was a key moment in that proof that was very important to notice. It was at this stage here when I knew that these are both less than epsilon, and when I added them together that gave me 2 epsilon. So what I wanted to do was go back here and adjust this number so that when I added it together later it would come out to epsilon. Now if you see a proof written as it's written on this page forwards, you're often like, well, why did we do epsilon on 2? But that decision is usually made later. So I normally leave a bit of space just in case it's easier to, just in case I need to adjust it later when I get there. At least I knew what I was looking for. I knew I needed to say what n was. I needed to be able to show that this was less than epsilon. So one of the nice things about the fact that it was convergent is that I could create a statement that had a capital N in it. And so I would be able to say, this is what n is. It's the n that is mentioned in the definition of convergence. And I can use it again to be part of the definition of Cauchy. So I'm not technically using the exact one in the definition of convergence. I'm using the next one out that makes it less than epsilon on 2. But we know there's one of those two, because convergent means that no matter which epsilon I pick, I can still find a capital N, including if I pick epsilon on 2. So in layman's terms, this means that if all of the terms of a sequence get closer and closer to a particular x, then they also get closer and closer to each other, which is what Cauchy means. In a complete metric space, if the terms of the sequence get closer and closer to each other, then they all get closer and closer to some other limit as well. Yeah. That's probably enough. I should probably relieve Nicholas from the Maths Learning Centre. But we can talk more about this as the days go on. Which day is your exam on?
Friday.